Okay, we're going to continue with the Chapter 5 material today and probably finish it if all goes well. My only reminder about this part of the course is that just like Chapter 2, Chapter 5 has 2 homework assignments associated with it. So the one that's going to be due this coming Sunday is Chapter 5 Homework A, but then that same day, Chapter 5 Homework B will open up as well. So make sure you do the correct one if you're trying to get your last attempts on the first one in on time, so don't make the same mistake that some of you made in Chapter 2. So there'll be 2 assignments, and I said we'll finish Chapter 5 today, so really you'll have all of next week too to sort of review that material as we get into the newer and material from Chapter 6. All right, so what we're going to start with today is continuing on with some examples of stoichiometry problems. So we learned the process for doing this last time, and we gave one example at the end of class before we ran out of time. And so let's just start with this to sort of solidify some of those approaches. All right, so what we have here is a typical setup for a stoichiometry problem. So we're describing the reaction to you. So we're saying that iron metal reacts with water to form magnetite and hydrogen gas. So magnetite is another form of iron oxide that's a little bit different than rust, but it's still iron oxide. And how many grams of water are required to react completely with 25.0 grams of iron? So the first thing we need to do is write the balanced equation. As we said last time, sometimes we'll just describe it to you. You have to make sure you arrange reactants and products correctly, and you also have to make sure you get the coefficients put in correctly. So here we have iron metal, which is just the element Fe, reacting with water. I hope you all know what the formula for water is at this point. So Fe plus H2O is going to be our reactants. So that's what's reacting, and then we're going to form, whatever you form is on the product side, so that's going to be Fe3O4, and hydrogen gas, which we're telling you here is H2. All right, so those are the reactants and products, 2 reactants, 2 products. As we said last time, when you're balancing an equation, find something that's fairly complex and set it to 1. So this compound here has 2 different elements, 7 total atoms in the formula, so we'll set that to 1 and try to balance everything else off of that. So with one of those, we now have 3 irons on the product side, so we'll put a coefficient of 3 there for Fe. With one of those, we have 4 oxygen atoms, so we need to have 4 oxygen atoms on the left side of the arrow, so 4 there takes care of that. And now with 4 waters on the left side, we have a total of 8 hydrogens, so we need a coefficient of 4 there to make sure that hydrogen is the same on both sides. So I went through that quickly, but that's always going to be the first step in stoichiometry. Review how to balance equations if that was a little bit unclear at this point. But you're, again, just making sure that the elements and the atoms on one side of the arrow are the same as what's on the other side. And so we can always double check ourselves, so we'll go through that a little bit more deliberately to start out with. So on the reactants and product side, we have to make sure we have the same number of each atom present. So we have iron as one of the elements present. On the reactant side, we have 3 elemental irons, so that's going to be a total of 3 equivalents or 3 moles of iron. On the product side, we have 1 mole of Fe3O4, but each of those has 3 iron atoms in the formula, so it's going to be a total of 3 on the product side as well, so those match. Hydrogen is the next one. We have hydrogen here in water, so there's 4 moles of water with a total of 2 hydrogen atoms each, so that's 8 moles of hydrogen. On the product side, we have 4 moles of H2, so again 4 moles, 2 hydrogens per mole, total of 8 moles of hydrogen, so those match up as well. And then for oxygen, we have 4 moles of water, which each have 1 oxygen in the formula, so that's 4 moles of oxygen. And then we have 1 mole of Fe3O4. The subscript tells us that there's 4 moles of oxygen in 1 mole of that compound, so that is 4 as well. So the reactants and products, all the elements match up on both sides of the arrow. That's how you would check yourself to make sure it's balanced. But again, as you do more of these, it should become pretty quick and pretty straightforward. So that's always going to be just the first step for a stoichiometry problem. So we have to get this part first to be able to approach the rest of it. So now what we're going to do is just do the conversions that are indicated in the problem. So as we said, we'd like to start with what we're given and then work our way to what we're looking for. So let's write out the equation again, since we'll need it here as well. So that's the equation we just balanced. I previously, as I said, I put the coefficient of 1 in explicitly before, but usually it would not be shown, so this would be an appropriate way to balance. Just remember that there is an implied coefficient of 1 there. And now what we're looking for is how many grams of water are required. So we're looking for grams of water, so that's what we're going to start with. And what we're given is a mass of iron that we're starting with. So in any stoichiometry problem, we will have additional types of stoichiometry problems coming up in the next chapter. In any stoichiometry problem, the first thing you want to do is convert to moles. So if we have a mass of an element, we can convert to moles using the atomic mass. So we're going to put the atomic mass in the denominator so that grams cancel out. That was not given to you here, but that's an element, so we can easily find it from the periodic table. So our periodic table, I always forget to load it before class, so give me a second. Fe is 55.85, and if I remember correctly, there it is. Atomic number 26, the mass, which is below, is 55.85. So that's going to be the atomic mass of iron to get us into moles. All right, so now we're in moles of iron, but we're looking for grams of water. So now when we want to convert from one substance to another, once we're in moles, we can use the coefficients to do that. All right, so we want to go into moles of water, which is the substance we're interested in, and we want moles of iron to cancel out. So for these, we just use the coefficients directly from the equation. So water has a 4 in front of it, so 4 is going to go up there. Iron has a 3 in front of it, so 3 is going to go down there. All right, and then again, writing out units is critical because we can't stop here because this is moles. We're looking for grams of water as the problem asks us, so we have to do one more step to go from moles into grams. And in general, we would use the molar mass for that, which in this case is given to us for water, 18.02 grams per mole. So 18.02 grams of water in 1 mole. So moles cancel out, and now we've gotten to the unit we're looking for, which is grams of water. So multiplying those all across. So in principle, you can do this stepwise. You can do one step at a time. Grams of iron into moles, moles of iron into moles of water into grams. But I like to write it out in one string. Saves you some time, saves you some rounding and all that stuff. So what we'll get is 10.8 grams for that. So that means if we want all of our iron to react completely, we need to add 10.8 grams of water to this reaction. Okay, so any questions on that? It's a typical mass-to-mass stoichiometry. Remember, we can use this same approach to do any relationship between any reactant and any product. So here it was, we're giving you an amount of one reactant, asking you to find the amount of the other reactant that reacts with it. But in the next example here, which I will leave for you to try on your own, as it actually says here, this time I'll stick to my word, is we're given the same equation, but this time when we react the 25 grams of iron, we want to know how many grams of hydrogen, H2, are formed. So I encourage you to try that one on your own, see if you understand what we're going, and not right now, but ideally after class so I can move on. But then I'll put the solution in the notes and the work to get there, and if there's anything that you missed, you'll be able to see that. But again, it's a very similar approach, just this time using one of the products as the substance we're calculating as opposed to one of the reactants. So you really don't have to change anything, just make sure you're using the correct coefficients and the correct molar masses. All right, but we're going to move on to the next topic here, which is limiting reactant. All right, so sometimes with limiting reactant, it's the concept that gets people a little bit confused. What exactly is this referring to? And so a limiting reactant is basically the idea that if you mix two reactants together and you're mixing them and they're not exactly in the right ratio as they would react with each other in the equation, then one of those reactants is going to limit how much of the product forms, and the other reactant there's going to be some left over. So an analogy that sometimes helps, and I think your book goes through an example like this, is a sort of a culinary analogy. So I'll do one with baking that I'll just sort of make up off the top of my head here. So a lot of people took up baking as a hobby during the pandemic. I was not one of them, but if you've ever done baking, you know that you have to follow pretty precise recipes. You'll have a certain amount of this ingredient, a certain amount of that ingredient, and you have to make sure you keep it right, or else you're gonna probably not come out the way you want it to. So let's say you're baking a loaf of bread, one loaf of bread, and the recipe requires 2 cups of flour and 1 egg. I don't know if that's reasonable or not, but let's just say that's the case. Okay, so 2 cups of flour, 1 egg to make 1 loaf of some type of bread. All right, if you have 4 cups of flour and 2 eggs, how many loaves can you make? 2, exactly. But what if you have 2 cups of flour and 2 eggs? How many loaves can you make? Someone said 0. Well, you can make one, and then you'll have, exactly, then you have 1 egg left over. So you would use the 2 cups of flour and 1 egg to make 1, and then you have 1 egg left over. So that's really what limiting reactant says. If you don't have the exact right ratio of your ingredients, one of those ingredients is going to limit how much of your product you can make. And that's exactly what happens in chemistry if we mix 2 things together, but they're not in exactly the right mole ratio. So there's, when you're doing a limiting reactant problem, and I'll get into how you know if you have to even go through this analysis or not, there's a couple ways to do it. So the way that your book does it, I'll just kind of describe it in words, and I'm actually going to do it numerically. I like my approach a little bit better. It's really a similar amount of work, but I think there's some advantages to the way that I do it. But what the book does is it goes through a couple different approaches. So one would be, typically what you'll do is determine the moles of each reactant. So the way that the book describes it works, and so if you like it, go ahead and use it. I'm not going to say it's wrong or anything. So let's say the 2 reactants are A and B. And then what you would do is how many moles of B are required to react with that much A. So in this case, what you're doing is you're doing sort of a stoichiometry calculation to say, well, okay, I have 2 reactants given. How much, if I know how many moles of A I have, how much moles of B are required to react with A? And for that, you use the stoichiometric ratio. So you do basically the stoichiometry problem. You just randomly choose one of your reactants and figure out how much the other one is required. But where it gets a little bit confusing is, okay, so how do I interpret this number? So you calculate an amount of B that's required, and you compare it to the amount of B that you actually have. And so if the amount you calculate is less, then the actual amount you have, see, it gets wordy just talking about it. So this is one of the reasons I don't like it, to be honest. So in that case, that means A is a limiting reactant. In other words, you have, in this case, too much B compared to A, so that makes A the limiting reactant. And then, of course, the opposite scenario would also apply. So if the amount of B that you calculate is more than the amount of B present, that means you don't have enough of reactant B, and that makes reactant B the limiting reactant. So this is one way to do it. Or the other way to do it is just calculate moles of product from both reactants, A and B. So in other words, figure out, okay, if I have this many moles of A, how much product forms? If I have this many moles of B that I'm given, how much product forms? And then the lower number that you get is correct and indicates the limiting reactant. So whichever A or B gives you the smaller amount of product, that is the limiting reactant, and the number that you calculate is the correct number for moles of product if that's part of what you're looking for. But again, what this essentially requires you to do, and I may have not worded it in the most concise fashion, so read your book if you can't follow what I'm saying here, but it requires you to do the problem twice. So you basically do the stoichiometry problem twice, starting with A, starting with B, and then depending on how the 2 answers compare to each other, you can figure out which is limiting reactant or not. So I'm not going to go through that in more detail because I don't really like that approach, because it's easy to confuse yourself. Do I pick the smaller number? Do I pick the bigger number? If the 2 numbers are different, what does that mean? It's a lot to think about. So what I like to do instead, it's sort of a shorter way. In most cases, it doesn't really save you a lot of work. But what it allows you to do is very quickly identify which reactant is the limiting reactant. So you can just do a very simple series of 2 calculations for each reactant, as I'll show you, and then you just compare those 2 numbers, and right away you know which one's limiting reactant. Because any other calculation you do for that problem, how much product forms or whatever, is going to always start with the limiting reactants. You have to identify that first. So I like to do it this way because then there's no guesswork involved. You just Figure out your limiting reactant as a first and additional step, and then from there you just go and solve the problem like you normally would. Okay, so here's the way that I'll teach it and the way that I'll go through it in class, which I encourage you to use if you like it. I don't usually lead you astray, but maybe sometimes I do. But I think in this case you're going to like the way I do it. Okay. All right, so what you're going to do is determine what's called the stoichiometric ratio for each reactant. Now let's define what that is, of course. We haven't seen that before. All right, so I'm going to abbreviate this as capital R. This is not really a standard definition, but that's just how I'll call it. And what you're going to do is you're going to take the moles of each reactant. So you have to calculate moles of each reactant, which is normally involved in any stoichiometry problem. And then you're going to divide that by the reaction coefficient for that specific reactant. Okay, so you always need a balanced equation. There's no shortcut around that. And then what you're going to do to find limiting reactant is if you have amounts of 2 or more reactants, so if we tell you how much of 2 reactants you have specifically, then you're going to calculate the moles of each of them, divide them by their coefficient. And the one that has the smallest value of R, the smallest stoichiometric ratio, is going to be your limiting reactant. All right. So again, calculating R doesn't really get you anywhere in terms of solving the problem directly, but it tells you immediately what the limiting reactant is. And so you don't have to guess or do extra work beyond that. You've already got your limiting reactant, and then anything else you're going to do in that problem is going to start from there. Now I'll abbreviate limiting reactant as LR in case that's not obvious. Okay, so you calculate the stoichiometric ratio for each reactant, however many you're given, 2 usually, sometimes more than 2. And then what you'll do is find the smallest of those numbers, and that will tell you what the limiting reactant is. And this is important, so I'll put it in red with a star next to it, because when you're then going through and doing the problem, whatever stoichiometry calculation you're doing, which we're going to learn, in this chapter is mostly going to be mass-to-mass stoichiometry, but you could do other variations as well. Any subsequent stoichiometric calculation has to start with the limiting reactant. And that's because the limiting reactant is the one that's going to react completely, and it's going to limit, as the name implies, how much product can form if you're trying to calculate that. So any calculation you do must begin with the limiting reactant in a situation where you have that to worry about. So then the question comes up, and I've kind of already answered it, but I'll do it a little bit more explicitly now. How do I know if I need to determine the limiting reactant? Because we did a couple example stoichiometry problems already, and we didn't even talk about limiting reactants. So why do we, in that case, we didn't need to worry about it, but in some cases we do. So how you know is pretty simple just by looking at the problem. It's if you're given exact amounts of 2 or more of the reactants. We usually won't do it for more than 2, just because we don't want to have you guys spending too long on these types of problems, but it could be more than 2. But if you know the amounts of 2 or more reactants, you need to determine which of those is the limiting reactant. All right, you can't just guess. You have to determine it using the approach that I outlined. All right, so that's going to be the case. And then in other situations, like we saw for the problems that we were doing earlier, if you're just given an amount for one reactant, or if you're explicitly told that 1 or more reactants is in excess, then you don't need to worry about limiting reactant. So if you're given an amount for only 1 reactant, or if you're starting your calculation with an amount of product, so we can give you stoichiometry problems where we say, we want to make this much product, how much reactant do you need? Or how much of another product forms. So if your problem is starting with a product amount, not a reactant amount, then you don't have to worry about limiting reactant. You can start the problem as normal. You don't have to do the limiting reactant nonsense, okay? Or business, I should say. It's not nonsense. All right, so it requires, again, a little bit of practice and a little bit of familiarizing yourselves with how these different problems are set up. But the first thing you need to do is look at the problem and say, okay, do I know the amounts of 2 or more reactants? If that is true, then you have to figure out which of those 2 is the limiting reactant. If we only give you the amount for one reactant, and we explicitly say that other reactants are in excess, we don't give you their amounts. Or again, if the problem is starting with how much product is forming, if we say how much water is required to form this much of the iron oxide, like in the previous problem, if that's the case, you're starting with a product, then you don't have to worry about which reactant is limiting. So you have to get familiar with that, but usually it's pretty clear from the way the problem is set up. There shouldn't be any confusion. You just have to remember to keep that in mind. So let's give you a typical limiting reactant problem. So we have this equation here, 2NH3 plus 5F2 forming N2F4 and 6HF. So this is a reaction that would be a little bit tough to balance, but we could probably do it. But at any rate, it's already given to us balanced, so we don't have to worry about that. But we want to know how many grams of N2F4, this product here, can be obtained from the reaction of 5 grams of NH3 with 15 grams of F2. Okay, now as we said, this is a classic limiting reaction problem because we're telling you how much NH3 we have, which is one of the reactants, 5 grams, and we're telling you how much F2 we have, 15 grams, which is the other reactant. So we know how much of both reactants we have, so we have to figure out which the limiting reactant is to determine which one we're going to use for calculating the amount of product that would then form. Okay, so that's going to be the first step, is determining limiting reactant. So we'll go through those steps kind of deliberately in this first example. So let's determine the moles of each reactant. All right, this is never a bad thing to do anyway in a stoichiometry problem, so we'll start with that. So for ammonia, we have 5 grams. And for each of them, we're going to just use the molar mass to figure out how many moles that corresponds to. So we want grams in the denominator and converting into moles, so we need to divide by the molar mass, which is 17.0 for NH3. So we get 0.294 moles of NH3. And then we're going to do the same thing for F2, the other reactant. We have 15 grams. And we're going to divide by its molar mass. So these steps should be starting to become commonplace now because we've done them so many times. Just mass into moles, just divide by the molar mass. So grams cancels out, and that gives us 0.395 moles of F2. Now what we have to remember is that this is not all we have to do to find limiting reactant. You can't just compare the number of moles and say, oh, the number of moles of NH3 is smaller, that must be our limiting reactant. Remember, it's not quite that simple. We have to also then divide by the coefficient. So the second step, which you could combine with the first step when you're doing these in reality, but I'll again spell it out more deliberately, is to determine the stoichiometric ratio. All right, so you can't just compare the moles. You have to determine this ratio R that we talked about. So the ratio for NH3 is the number of moles, 0.294, divided by the coefficient. The coefficient from the balance equation for NH3 is 2, so we divide that by 2 and we get 0.147. When we do the same thing for F2, we have more moles of F2, so the numerator is 0.395, but we're going to divide that by a coefficient of 5 instead, and so the stoichiometric ratio for this is smaller. Okay, so even though there are more moles of F2, its ratio is smaller when we divide by the coefficient, so this is the one that's going to be our limiting reactant. All right, so again, those series of steps, moles divided by coefficient, and calculate moles divided by the coefficient, that allows you to quickly identify that F2 is our limiting reactant. So now whatever else the problem is asking, in this case it's asking how much product can form, we're going to start with F2 as our starting point. Okay, so that's going to be the next step then, is to take this forward, starting with the limiting reactant F2. So step 3 in this is going to be to just do whatever calculation we're asked to do, making sure we start with limiting reactant. So we could, again, we could start with grams of F2. So what we're looking for, let me get that first. We're looking for grams of N2F4. That's our ending point here. And again, we're going to start with F2 because that's our limiting reactant. We could start all the way back with the mass of F2 that we're given directly in the problem, or we already calculated the moles. That's going to be our first step anyway, so we can just start with that number as well. You'll get the same answer either way. It's one less step because we've already done this conversion into moles. So I'll just start with that. 0.395 moles of F2. That would be the first number you would calculate anyway. And then once we have that, we can get into what we're looking for, which is grams of our product N2F4. So we're already in moles of our limiting reactant, so to get moles of product, we just have to use the stoichiometric ratios from the balanced equation. So we want moles of N2F4, and we want moles of F2 to cancel. So for that, we're going to just use their coefficients. 1 in front of N2F4, no explicit coefficient. 5 in front of F2. And that gives us into moles of N2F4. And then finally, what we want is grams of N2F4. We gave you the molar mass is 104. So we're going to use that to go back into grams. So we want moles to cancel. And we want to get into grams. So we're going to put the molar mass in the numerator this time, 104.0 grams in 1 mole. So moles cancel, and that gets us to grams, which gives us to 8.22 grams of N2F4. All right, so that's how much product forms. If you had started with NH3, you would have gotten a bigger number, which was also then incorrect because F2 is our limiting reactant. It's going to determine how much of the product we can form. So that's kind of the typical approach. One word of caution on doing it this way that I've taught you is once you find these stoichiometric ratios here, 0.147, 0.079, identify the smaller one as limiting reactant. Once you do that, these numbers are completely useless, okay? So you want to throw them away after that. So we didn't use this 0.079 as a starting point. That's just a ratio specific to that reactant. It's not necessarily going to be relevant to the stoichiometric calculation we're doing. So the best thing to do to save yourselves any mistakes is once you find these numbers, you use them to figure out the limiting reactant, and then you throw those numbers away. You don't want to use them anymore. So we went back and started with moles of reactant to do the actual stoichiometric calculation. That's the proper way to do it. All right, so that's my one word of caution about that. Now the next part of this question, which is the same problem, is how many grams of excess reactant remain after the reaction. So the limiting reactant is the one that reacts completely. So after the reaction, there will be 0 limiting reactant left. So we determined that F2 is our limiting reactant. So once the reaction's over, we form some N2F4 and HF. There's going to be no F2 left over because it's our limiting reactant. But the other one that's not limiting is in excess, meaning that some of it will be left over. So NH3 is going to be our excess reactant. So the way that we do this to find excess reactant is sort of a two-step process. We're first going to figure out if we know how much limiting reactant we have, how much NH3 is required to react with that, and then we're going to do by difference how much is left over. So the first step is to figure out how many grams of ammonia, NH3, were consumed in this reaction. All right, so as we said, we're starting with the same starting point, moles of limiting reactant. So that's how many moles of F2 we have, and we're going to figure out how much NH3 reacts with that many moles of F2 using stoichiometry. So this calculation doesn't look too much different, it's just using 2 reactants instead of a reactant and a product. So we're trying to figure out how much NH3 is consumed with that much F2. So we want the coefficients arranged as such, so the coefficient for F2 is 5, the coefficient for NH3 is 2. So that's moles of NH3, and then what we're going to do is we want to get into grams of NH3, since that's the amount that we're starting with. We told you that we started with 5 grams of NH3. That's in the first part of the problem. So we're going to use its molar mass to get the mass of that reactant. So 17.0 grams of NH3 in 1 mole. Okay, so what this number tells us is that 2.69 grams of NH3 were consumed by reacting with the F2, which is our limiting reactant. So that's how much NH3 was consumed, but that's not how much is left over, that's how much went away during the reaction. To figure out how much is left over, we have to subtract from the original amount. So the original amount of NH3 was 5.00 grams. That's how much we put in. 2.69 grams reacted, so the rest is going to be left over. So the excess reactant, this is our key second step now, if we want to find the amount of excess reactant, is we take the amount that we started with, which is 5 grams, so that's our starting amount, and we subtract the amount that was consumed, which we just calculated to be 2.69 grams, and that leaves us with 2.31 grams of NH3, which will be excess, leftover reactant that doesn't react to form product, okay? So when you do a limiting reactant problem, you also have the possibility, as I showed here, of calculating how much of the other reactant is left over once you know what the limiting reactant is. So these are sort of, two variations on the same problem. We could ask you for, either of these in a typical homework problem or exam problem. All right, so any questions on limiting reactants, how to calculate them, how to use that information in a problem like this? All right, let's just do one more example. This one I think is a little bit even more complicated. Okay, so here we have a reaction now with 3 reactants and 3 products. So 3N2O, 4 sodium, and again ammonia, reacting to form sodium azide, 3 sodium hydroxide, and 2N2 gas. So we're mixing together all 3 reactants. We're giving you amounts of all 3. 5.25 grams of N2O, 5.0 grams of sodium, 2.57 grams of NH3 are combined. So we gave you the amounts, in this case, for all 3 reactants. So anytime you have the amounts for 2 or more reactants, we have to figure out the limiting reactant, and that's actually the first question that this problem is asking. What is limiting reactant? So for each one, we're going to find the stoichiometric ratio. So it's going to start with moles. So for N2O, we have 5.25 grams, and we're going to divide by the molar mass to get into moles. So the molar masses here are given, so it's 44.01 for N2O. So we have 0.119 moles of N2O. That alone does not tell us if it's limiting reactant, so we're going to calculate its stoichiometric ratio R, which is going to be that number divided by the coefficient. So the coefficient for NO2, this equation was already balanced for us, so we don't have to determine that. It's going to be 3, and so that's going to be, what did I do wrong? Oh, that's right, 0.040, just to keep 2 decimal places. All right, so that's going to be the ratio for N2O. We'll do the same thing for sodium. Calculate the moles first. This is all mass to moles, so it's just going to be dividing by the molar or atomic mass. So we have 4.05 grams of sodium. Its molar mass is actually its atomic mass because it's an element, but that's given to us here, so we don't have to look it up. So that would be 22.99, same number you'd get off the periodic table. And so we have 0.176 moles of sodium, and its stoichiometric ratio is going to be that number divided by its coefficient, which is 4, which is just a little bit bigger, 0.044. All right, so you do want to keep at least a couple of significant digits just to make sure you can distinguish numbers that are close. So here we got 4,4, here we got 4,0, so they are a little bit different from each other. And then finally for NH3, the last reactant, it's going to be 2.57 grams. And we're going to divide by its molar mass of 17.03. 0.151. All right, so that's how many moles of NH3 we have, and then the stoichiometric ratio for NH3 is that number divided by the coefficient. Gosh, sorry, getting a little bit out of room here. So it's 0.151, and the coefficient for NH3 is not shown, it's just 1, so the stoichiometric ratio is that same number. All right, so the smallest of these 3 numbers is our limiting reactant, and by a little bit, this one's going to win out, so this is our limiting reactant. All right, so the first question is what is limiting reactant, and that would be N2O. The answer we could have easily eliminated is NaN3 because that's a product. You're never going to have a product as a limiting reactant. That doesn't make any sense. So, but in this case, there's 3 reactants. We had amounts for all 3, so we had to go through the calculation for all 3 to identify the limiting reactant. So any questions on that? All right, the next problem then is how many grams of sodium azide, NaN3, are theoretically obtained, meaning how many can form if we have this much reactants present. So we have to start this calculation with the limiting reactant. So anytime we're calculating an amount of product that forms, the calculation starts with our limiting reactant, which we just identified as N2O. All right, so we're looking for grams of NaN3, and the calculation is going to start with our amount of our limiting reactant. As we said in the last problem, you could just use the mass of the limiting reactant, 5.25, as your starting point, or since we already went through and determined the moles as part of this first step here, we can just use that number directly. It'll save us an additional step in this part. So we'll start with moles of limiting reactant. Since we already have that number, you can always start with the moles. It's a acceptable starting point for any stoichiometry problem. And then what we're going to do is figure out the mass of product. So once we're in moles of reactant, we can calculate moles of product by using coefficients. So moles of sodium azide in the numerator, moles of N2O in the denominator, and we look at the coefficients. So it's going to be 1 for NaN3, 3 for N2O. Okay? So that's going to be the ratio of those two, which gets us into moles of product. And then to get back into mass, we use the given molar mass. So we're going to multiply by molar mass this time, grams per mole. That comes out to 2.58 grams. All right, so if you had started with the wrong limiting reactant, you would get the wrong number as your answer. So it would be larger than this and not one that we're looking for. All right, but again, once you have the limiting reactant, then the stoichiometry calculations are exactly the same as what we've already covered starting last time. So it's just an additional step to find what your limiting reactant is. All right, any questions on that? All right, the last, sorry, go ahead.
One of the questions was to find the excess reactant.
Yeah, so any problem that asks for excess reactant would also require you to identify what the limiting reactant is, because whatever is not the limiting reactant would be the excess reactant. So actually in this case we'd have 2 excess reactants. We'd have sodium and NH3 would both be in excess, and so you could in principle calculate the amount left over for each of those. It would specify which one to calculate if we were asking you to do that in a problem. So if you have more than 2 reactants, then one is still going to be limiting. The rest, however many else you have, will be in excess. Yeah.
The one
NaN3?
Yeah, the coefficient from the
It came from the equation. If there's no coefficient shown, that's implied to be 1. So it's not written there, but it is a 1. All right, other questions? All right, the last major stoichiometry topic we'll cover in this chapter, there's more to come, but in this chapter is going to be what's called percent yield, which is a function of 2 things. Okay, so there's, again, this is just one additional step we can add to a stoichiometry problem. It's still, the same steps we learned up until now are going to still be valid, still be required, but then there's one more thing we can talk about, one more concept that's related to stoichiometry and chemical reactions, which is called percent yield, and it's dependent on 2 things, theoretical yield and actual yield. So theoretical yield is the maximum amount of product that can be obtained if all of the limiting reactant is consumed. Basically, this is what you calculate in a stoichiometry problem. So in the last 2 problems, we calculated how much product forms once we identified our limiting reactant, and the amount that you calculate is what's called the theoretical yield. That's the most amount of product that you can get from that reaction. All right, and so theoretical yield is just what you calculate from stoichiometry, how much product can form in that reaction, where you have to know what the limiting reactant is, start from there, figure out how much product forms. Now the actual yield is the amount of product that is actually obtained experimentally. Now you can't calculate actual yield starting from scratch. This is an experimental number. So you run a reaction in a lab, you collect all the product from that reaction, and you measure how much there is. And in most cases, it's not going to be exactly equal to the theoretical yield. It's going to be a little bit less than that, or a lot less than that sometimes. All right. So this is an experimental parameter. You run a reaction in a lab, you collect the product, you weigh it out or measure it out, however you measure it, and you compare it to the theoretical yield. And as I said, it's going to be equal to or less than the theoretical yield. That's your actual yield. Now, why would it be less than the theoretical yield? Well, there's a few reasons for that. So one would be, experimental losses, what we would call in colloquial terms human error. I don't like that term, but essentially you're running the reaction and you spill some of the product, or you're trying to collect it from whatever reaction flask it is, and some of it is stuck to the walls of the flask. I mean, there's a lot of possible ways, but basically just a physical problem with collecting all the product. The other one that sometimes happens is called side reactions. So this is where your two reactants can possibly react at the same time to form something different than that product. That's a different reaction altogether. Or sometimes the product that you form reacts with one of the reactants to form something else as well. So basically this is two reactions happening at the same time, so you're going to consume some of your reactant or possibly consume some of your product in that other reaction that's also occurring. So that's called a side reaction. And then the third one, which is not really going to be, we're not going to talk about any of these in great detail in this class, but the third one is a reaction that doesn't go to completion. Meaning you mix together the reactants, you wait for the product to form, but at the end of some long period of time, you form some of the product, but you still have some reactants that haven't reacted with each other yet. And that's what's called, if it's often referred to as an equilibrium, is one way to think about that. So you'll learn about that in Chem 2, reactions that don't go to completion, and how to analyze and think about those. But the point is, your actual yield is less than your theoretical yield in almost every case. It's never going to be more than it, obviously. And there's a lot of reasons why that can be. And there's listing a couple of them here concisely to point them out. So then what you would calculate from these is what's called your percent yield. So this is going to be the actual yield divided by the theoretical yield. Then you multiply that by 100, because every time, remember, percent is always out of 100. All right, and again, your percent yield will always be less than or equal to 100. If it's a greater than 100% yield, then you did something wrong in the calculation, or if you're doing it in a lab, you did something wrong in the experiment. Okay, so there's always going to be a number less than or equal to 100. And so that's another thing we can calculate. Now, as I said, you cannot determine from just the typical information in the problem what the actual yield is. That's an experimentally measured value. So if we want you to calculate percent yield, we would have to tell you what the actual yield is for that experiment. In the problem, this is not a laboratory course, so we would give that to you. Alternatively, remember that we can do a little bit of algebra as well. So if we can give you the percent yield, and you could then calculate what the actual yield would be from that. So basically just rearrange this equation. Percent yield is actual yield over theoretical times 100. Rearrange the equation and solve for actual yield if you know the percentage and you know the theoretical. So we can ask you that in a couple different ways, but in reality there's only going to be only one thing that's unknown in this type of problem. Either the percent yield, which you'll have to calculate, or the actual yield if you're given the percent yield. All right, so let's see how this works in practice. So we're going to do a pretty simple reaction here where we make this compound here, WCl6, tungsten. It's called tungsten hexachloride, even though it's not really the correct nomenclature for that. It should be tungsten 6 chloride. But anyway, it's prepared by the reaction of tungsten, which is W, and chlorine gas, which is Cl2. And so let's say we go in the lab and do this. We combine 5 grams of tungsten, 6.75 grams of chlorine gas, and at the end of the reaction we obtain 5.92 grams of WCl6. What is the percent yield for this reaction? So this is a typical percent yield problem where we're giving you amounts of one or more reactants, so you're going to use those to figure out the theoretical yield. We're telling you how much is actually formed or actually collected at the end of the reaction. That's your actual yield. So again, this number here is your actual yield. and then we're going to ask for the percent yield by, again, dividing the actual by the theoretical. So we have to calculate the theoretical yield. That's almost always going to be the case in these problems. You calculate the theoretical yield using stoichiometry. All right, so the equation here is pretty simple. It's W plus Cl2 to form WCl6. And we need 6 chlorines on both sides. So that means we need a coefficient of 3 over there. So a pretty simple equation, 1 to 3 mole ratio. But in this problem, as we did in the last couple, we gave you amounts of both reactants. So before we calculate theoretical yield, we have to figure out what our limiting reactant is. Theoretical yield is always determined from your limiting reactant, just like any other stoichiometry calculation. All right, so we're going to do those few steps. We're going to calculate for each reactant the moles and the stoichiometric ratio. So we have 5 grams of tungsten. It's an element, but we're giving you the atomic mass, so you don't have to look it up on the periodic table. You might be wondering why is tungsten abbreviated as W. It's because it's from, I believe, a German word, Wolfram, or something like that. So the element was originally named in a different language that begins with a W, but they kept it as W when they renamed it as tungsten. So we're going to get moles of each reactant, that's grams per mole, dividing by the atomic mass. 0.0272, and the stoichiometric ratio is going to be that number divided by the coefficient. The coefficient for W, there's none listed, it's just 1, so it's going to be the same number. We do the same thing for the other reactants. So again, it's a series of steps you have to do. It doesn't really get you directly to the answer, but it quickly identifies the limiting reactant. So 6.75 grams of Cl2 is how much chlorine we have, and then we're going to convert that into moles using its molar mass, which is also given to us. 70.9. All right, and so that comes out to 0.0952, and the stoichiometric ratio for Cl2 is that number divided by its coefficient, which is 3 in the balanced equation. All right, so those are the two stoichiometric ratios. The smaller of those two is for W, tungsten, so that's going to be our limiting reactant. Okay? So we've identified the limiting reactant, and now the next step to getting percent yield is to calculate what the theoretical yield, because percent yield, as we said, is the actual yield, which is given, divided by the theoretical, multiplied by 100, so we need to calculate the theoretical yield. All right? So that's going to be the next step we'll go through. Same equation, and now what we have to do is calculate the theoretical yield. And again, theoretical yield is just a fancy term for the amount of product we determine using stoichiometry, how much can possibly form using the stoichiometric calculations that we're learning. So we're looking for how much WCl6 can form, and we're going to start with moles of limiting reactant. The limiting reactant is tungsten W, and there's 0.0272 moles. So that's going to be our starting point, moles of limiting reactant. And then we can get moles of product. It's a 1-to-1 mole ratio. So 1 mole of WCl6 is going to form for every 1 mole of W that reacts. So that number is the same number of moles of product. And then to get grams of product, we're going to use its molar mass, which is given here as 396.54. So 396.54 grams of that product for every 1 mole. All right, and so that gives us a number of 10.8 grams of WCl6. All right, and again, that number is our theoretical yield, the most amount of product we can get, starting with this amount of the two reactants that were given, okay? So that's the theoretical yield, the maximum amount that we can form. And then finally, once we have theoretical yield, the last step, as we said, which is just an addendum onto this, is to calculate percent yield, which is usually the easiest part of the problem once you have all the numbers. So it's going to be actual yield divided by theoretical yield multiplied by 100. All right, so we put the numbers in. Again, this number here that we're given is our actual yield, the amount of WCl6 that we get at the end of the reaction, an experimental number that we would measure. The theoretical yield we just calculated is 10.8 grams. And we just multiply that by 100. And we get 54.8%. All right, so that means we got 54.8% of the product that we could have gotten if everything had gone perfectly. Now, is that good? Is that number bad? It just depends on the context. Some reactions just inherently don't work very well, and you're lucky to get that much. Other reactions, work really well, and if you get a lot less than your theoretical yield, then that probably means you messed something up. So it really depends on the context. This specific one, I don't know if that's a good number or not, to be honest. But that's how we would do it. It's just one step at the end to calculate percent yield once you have your theoretical yield and the given actual yield that you're provided. All right, so any questions on percent yield? Okay, so I think that takes us to the end of chapter 5. So any last questions on stoichiometry before we leave it for a bit? So there's going to be more stoichiometry in chapter 6, but it's not the only focus of that chapter. So we're going to come back to stoichiometry towards the end of this chapter. I think I might do chapter 6 in a little bit different order than the book does. I think the book kind of like sprinkles in stoichiometry throughout the whole chapter as it introduces different topics. But in reality, the stoichiometry you do in chapter 6 is pretty much all the same from topic to topic, so I'll kind of like save that towards the end and bring it all in together. But at any rate, we're sort of ahead of the homework assignments anyway, so you have plenty of time to piece all that together. But let's go on and start chapter 6 now with some definitions and some concepts. Okay, so chapter 6 is all about chemical reactions again, but it's chemical reactions that happen in a solution, which means that your reactants and products, or at least some of them, are dissolved in a liquid of some sort. So we have to get some definitions related to that as well. So a solution is sort of another synonym for a homogeneous mixture. And it's going to be of two or more substances. So we're talking about mixtures now. And what we mean by homogeneous is that it looks like a single phase. You can't tell easily that there's two things mixed together just by looking at it. So a classic example of a solution is salt water. You guys are all familiar with that if you've ever gone to the beach. It's salt and mostly sodium chloride, but some other things as well. Dissolved in water. If you look at a glass of salt water, you cannot tell by looking at it that it's salt water. It just looks like water because everything is homogeneously mixed together into a single phase. Now, solutions technically can involve any state of matter, so you can have solutions of gases, you can have solutions of, in some cases, solids, like metals will form solutions with each other that are called alloys. But the most common one that we're going to talk about in this class is one that involves a liquid. So a liquid is going to be dissolving something else, usually a solid. So that's the typical solution, especially in this chapter. That's going to be the relevant one. So it usually involves a liquid, when we use that word solution especially. All right, and as we said, examples would be salt water. Most beverages are solutions. Especially if they're transparent, like a juice. Carbonated beverages, they sort of are, but some of the gas that's dissolved sort of escapes, so they're a solution, but then the components separate. But anyway, most beverages, as we said, solutions can involve gases as well. So the air that you breathe is a solution involving many gases, primarily nitrogen and oxygen, but a bunch of minor ones too, carbon dioxide, argon, tiny amounts of probably helium and things like that too. So there's a lot of different gases around you, and air would be a solution as well. You can't tell that there's more than one thing in the air just by looking at it. And then another common solution is gasoline. So gasoline is not a single pure substance, it's a mixture of a lot of different substances that are all sort of dissolved together. Okay, so those are examples of solutions. Now, in a solution, you have two components, and especially when we're talking about liquid solutions that we're going to be dealing with in this part of the course, this is the terminology we use, solute and solvent. So the solute is the minor component, whatever you have less of. But in the case of a solution where something is dissolved in water, like we're dealing with in chapter 6, it's pretty obvious what the solute is whatever is dissolved in the water. So in salt water, salt is the solute. It's what you're dissolving in the water. Okay? And then the solvent would be the major component of a solution. Again, this term is used primarily for liquid solutions. So this would be what is doing the dissolving, what is dissolving the solute. So this would be the substance that does the dissolving, usually water, and for the chemistry we're talking about in this course, it will probably be 100% water. All right, so again, in a liquid solution, your solvent will be the liquid itself, which is usually water. And then when we have a solution that's dissolved in water, this is not really, I'll put a little dotted line between this. It's a separate term, but related. When you have a solution dissolved in water, we call that an aqueous solution. Some people say aqueous, but I say aqueous. I don't know what the correct one is, or maybe they're both correct. But anyway, when you have a solution that involves dissolving something in water, we call it an aqueous solution. So salt water is an aqueous solution of salt, whatever type of salt you have, usually sodium chloride. So that's what I mean by aqueous solution, meaning the solvent is water. All right? So that's kind of some definitions. Now to go back and review a little bit, why is water particularly good at dissolving things? And with the types of substances that it dissolves, especially in this chapter, are going to typically be ionic compounds or very polar covalent compounds like acids. So why is water able to dissolve them? Well, water itself is polar. So this is again a review of probably chapter 4 material. Why is water polar? We also told about the joke that I gave earlier. If you have a brown bear and a white bear dissolving or jumping in water, which one dissolves first? Anyway, but water is polar, so it dissolves polar things very well. So we have to understand why that is, and then we'll talk about how water dissolves things here in a little bit. So again, just to review some things we've already learned. We know that oxygen is more electronegative than hydrogen, so water is H2O, and so the bonds in water are polar because there's a significant electronegativity difference between the two elements. Oxygen is the second most electronegative atom on the periodic table behind fluorine. Hydrogen is quite a bit less electronegative. It's still a nonmetal, but it's quite a bit less electronegative. Now the other important part is the bent shape of water. And so you have these two OH bond dipoles, but they don't cancel each other out because they're in a bent arrangement. If it was linear, then they would cancel and you wouldn't have a dipole moment for the whole molecule. But in this case, it's bent. And so that's what these diagrams are sort of showing over here. This one in particular. You have two bond dipoles pointing towards the more electronegative oxygen atom. It's a little bit small on your screen, but you should be able to see those two arrows. And then in net, there's a dipole pointing from the bottom to the top because those two arrows, when they point together, they reinforce in the vertical direction as it's shown here, and you get this net dipole moment. And so what you have when you have a net dipole moment is you have regions of negative and positive charge. So water molecule has negative and positive poles, if you want to use that terminology. But essentially that's what this sort of what's called a space filling diagram is showing here. This is where you sort of show the full sizes of the atoms in relative form. And you can see that you have a region of negative charge, which is shown in red towards the oxygen, and then a region of comparatively positive charge towards the hydrogen atoms on the bottom, which are shown in blue. And so this is what's called an electrostatic potential map. You don't need to know the term, but it shows where you have negative and positive charges unequally distributed around this molecule. It's not a full negative and full positive charge, that's why it's labeled as delta minus and delta plus, but it's a region where you have more electron density up here and comparatively less electron density down here, so you have a little bit of an imbalance or an unequal distribution of charges. That's what makes water polar, and that fact is very important to how water dissolves things. I forgot to pull up these videos ahead of time, so let me see if I can get them for you and hopefully not crash my tablet in the process. So we're going to watch a couple of videos that will show us exactly how water dissolves different substances. So we're going to start with ionic compounds, and if the video doesn't work, I don't even know if Viddler still exists as a website. I think it's going to go for us. So here's what we're going to see. So we're starting with, this is sodium chloride. As we'll learn in more detail later in the course, again, my laser pointer doesn't work on the web page of the video, but what I'm pointing at is this blob here of positive and negative charges. So as we'll talk about in chapter 9, when you have a solid ionic compound, you just have alternating cations and anions arranged in three-dimensional space, like into a big cube, basically. So that's what we're showing here. This is sodium chloride, and then these little water molecules are going to come in and dissolve that sodium chloride. So when an ionic compound goes into water, so we're going to do an ionic compound first. Come on. Seems like it's halting a little bit, but we'll get there. All right, so this is basically it's not an interactive simulation, but a simulation. So we're putting salt in water. You guys know how that works. The salt goes in. You don't really see it when it's dissolved. It looks like just pure water, as we said. But let's look at the sort of microscopic level of what's happening. So they're going to eventually zoom in. They're a little bit annoyingly slow with this, but here we go. So the water molecules come in and they're going to surround all the individual ions, and they're going to grab them and just pull them into the solutions. They're going to separate the positive and negative ions from each other. So that's what happens whenever you dissolve an ionic compound from water. The positive and negative ions, which are held together by relatively strong ionic bonds in the solid, they get broken by the water surrounds it. If you look closely at what's happening, for each of the green ones, which is the chloride, you can see that the hydrogen atoms on water, which have the positive charge, are aligning around that. And then for the sodium, let's go back a little bit and see that. For sodium, you can see that the oxygen atoms on water are surrounding the sodium. The negative part of the water molecule is surrounding the positive region of the ion. So it's, again, that opposite charge is sort of attracting each other. So that's what happens at a microscopic level. You have, for an ionic compound, now let's look at a covalent compound. So methanol, CH3OH, is a polar covalent liquid, but it will also dissolve in water. So if you mix methanol with water, methanol looks a lot like water. When you mix them together, you can't tell that they're both there. So let's see what happens at the microscopic level for that. So the key difference with a covalent compound is you don't have distinct cations and anions anymore. It's just covalently bonded atoms. You're going to often have polarity, as we talked about, with regions of negative and positive charge, but you don't have discrete ions. And so when you dissolve these in water, you're going to have the water molecules surrounding the methanol, CH3OH, which is shown here, but you're not actually going to pull it apart and separate it into ions. So the water molecules are going to come in. There's already some interactions between the methanol, which again we'll talk about later in the course, but the water molecule surrounds those and pulls them apart from each other. But you'll see this time that the molecule is not breaking up. You're not forming positive and negative ions. You're not breaking any bonds. You're just surrounding it with water molecules, separating the molecules from each other, and that's sort of the process of dissolving something at the microscopic level. So there's a key difference between ionic compounds and covalent compounds at the microscopic level when they dissolve in water. All right, so we got through that without crashing, so let's go back and just write a quick summary of that, what we saw there. So in ionic compounds, the ions separate in solution. Again, the positive and negative ions go their separate ways and are both surrounded by water molecules and pulled into solution. In covalent compounds, there's no bond breaking when you dissolve it in water. So in covalent compounds, the molecules are surrounded by water. There's interactions between the partial positive and partial negative charges that those polar molecules all have, but you're not pulling it apart or separating it anyway. You're just surrounding it with water. Okay, so that's what happens at the microscopic level. And then what this leads to is some key properties of ionic solutions. So that's the difference between them, ionic compounds and covalent compounds when they dissolve. How does that relate to their properties then of these solutions? And the key property we're going to talk about, okay, which one? This one I probably have the harder time pulling up. Hang on a second. I need to probably try to select this link. Well, we're a little bit ahead of schedule, so we're doing okay. Okay, so let's see if this works. I gotta get the selection. That'll be close enough. All right, let's put that in here. No? Come on. Sorry, usually I remember to pull these up before class, and today I was bad about that. All right, this should work now. All right, so let's see if this one pulls up. Okay, so this guy, oh really? Okay. Okay, so this guy is a character, and he's going to show us some different properties of solutions that he has. And what he's going to be measuring is the conductivity of the solution. Do they conduct electricity? And he's going to basically do that by connecting a light bulb through the solution. So if you put it in tap water, which has some things dissolved in it, you see a little bit of lighting up. If we go to pure distilled water, nothing happens. So if you have pure water, they don't conduct electricity. Now let's look at some different solutions. So here's salt water, sodium chloride. You get really bright lighting up. So salt water, which has ionic compound dissolved, conducts electricity really well. If you have HCl, which is an acid, we'll talk about those later, they conduct electricity. Here's a base, another ionic compound. So what we can see is that for ionic compounds and acids, they conduct electricity. But here's sugar dissolved in water, nothing happens. So a covalent compound like sugar, there is no conductivity. Vinegar, which is what we call a weak acid, again, we'll talk about that a little bit more. You get some conduction, but it's not as bright as the other ones. And then here's another alcohol dissolved in water, very similar to the one I showed you, no conductivity. All right. So, and then here's an ionic compound that doesn't dissolve in water. So this is ionic, but it's not dissolved, as you can see, and you can see that it's not conducting electricity. So basically what this experiment here shows us, so that guy is done. You can imagine the sound on that is quite a wild ride, which is why I didn't have it on. So what this shows us is, depending on the type of substance you dissolve in water, you're going to have different conductivity for your solution. Okay, so the key property that results and that is sort of distinct between ionic compounds and covalent compounds in solution is whether or not they conduct electricity. All right. So we'll talk about ionic compounds and acids in water conduct electricity. So he did sodium chloride, he did some acids like HCl, and he did a base, sodium hydroxide, which is also an ionic compound. So ionic compounds dissolved in water conduct electricity, but only when they're dissolved. We saw the one example at the end where there was an ionic compound, barium sulfate, that didn't dissolve in the water. Some ionic compounds don't dissolve very well, as you'll learn in Chem 2. And in that case, there was no conductivity because it wasn't dissolved. And so a solution that conducts electricity, whether it's an ionic compound or an acid or any solution that conducts electricity, is called an electrolyte solution. So the term electrolyte also has sort of a context in human health, as you might be aware of. But when we're talking about it in a chemistry standpoint, it's a solution that conducts electricity. It's called an electrolyte solution. All right, so that's what we mean by an electrolyte solution. And again, that's determined by the type of compound that's dissolved in water. So within electrolytes, you have a few subcategories, strong, weak, and then also there's what are called non-electrolytes. So strong electrolytes are ones where when you dissolve them in water, you get a lot of ions separated in solution. So to have electrical conductivity, you need ions in solution. And so the types of compounds that would dissolve in water and produce ions are the ones that would be classified as strong electrolytes. So these are going to be typically your soluble ionic compounds. Any ionic compound that dissolves in water would be a strong electrolyte. Because ionic compounds, as we saw when they dissolve in water, they completely separate into positive and negative ions. And then the other category that would classify as a strong electrolyte is what's called a strong acid. The sort of distinction between strong acids and weak acids is more important in Chem 2 than it is in this class, but for now you need to remember what some of the classic strong acids are, because these would also be strong electrolytes. So HCl, the one we saw in the video, nitric acid, HNO3, sulfuric acid, H2SO4, perchloric acid. These are some of your common classic strong acids. And what happens when you dissolve any of these compounds in water, they also separate into ions. It's not as obvious because they're covalent compounds, but when you have acids that dissolve in water, if they're strong acids, the H plus more or less separates as an ion, and then whatever anion is left. So for HCl, when you dissolve in water, you get H plus separated by surrounded by water, and you get Cl minus separated. So they kind of behave the same way as ionic compounds in that respect. And the net result is that all of these strong electrolyte solutions conduct electricity very well. So all the solutions in that video where you got really bright lighting up of that bulb, meaning that the conductivity was high, those would all be classified as strong electrolytes. Weak electrolytes are ones where they partially break down into ions. I guess there's two others I should mention as strong acids. They're closely related to HCl, but the ones below it, HBr and HI, should also be there too, I suppose, in case you see them. But then compounds that partially break down into ions are called weak electrolytes, and they would weakly conduct electricity. So again, this is one of those topics where really all the details won't come until you take the next course in this sequence, Chem 13-12. But for now, we just need to know the basics. In some compounds, when you dissolve them in water, they're going to partially separate and form some ions, but most of the molecules are going to stay together, and those are called weak electrolytes. They don't completely break up into ions, but they do to some extent. And so the category of compounds that would fall into this category for our purposes are going to be weak acids, which would be any other acid that I didn't list above, more or less. There are other strong acids, but those are the common ones, and pretty much any other ones you'd see. So like acetic acid was the one that was in the video. Phosphoric acid, H3PO4, common weak acids. So any other acid that's not listed up here. And then also weak bases. Now for our purpose, the only weak base you need to know about is NH3. There's many others, of course, but that's the only one you'll see in general chemistry typically, ammonia. Okay, so those are what are called weak electrolytes. They partially break down into ions. They form some ions in solution, but they're not completely broken apart, so they don't conduct electricity as well. In other words, the more ions you have dissolved, the stronger the conductivity of the solution. And then the last category is non-electrolytes. These are ones that have no electrical conductivity. And so when you dissolve a covalent compound in water, this is what you get as a non-electrolyte solution. So any covalent compound that's not an acid would fall into this category. So non-acidic or non-basic covalent compounds would be non-electrolytes. So these would be things like alcohols, which are something that end in OH. So usually it would be like, let me give you a couple real examples. So the one we saw in the video was CH3OH, methanol is an alcohol, or just a longer carbon chain with an OH at the end. Those are called alcohols if they just end in OH. Or sugars, which we're not going to give the full formula and structure, but sugar molecules, fructose, sucrose, all the ones you might learn about in bio or biochemistry class, those would all be covalent compounds as well. All right, so I think instead of rushing into the next topic, I'll stop there. So that's, again, the conceptual basis of dissolving things in water. What we're going to start talking about next time is a more quantitative aspect. So how do we quantify how much substance is dissolved in a solution, sort of a new relationship involving moles, and then getting into different types of chemical reactions that happen in aqueous solution. So we'll get to all that next week. We finished chapter 5, so you're good for really the next 2 homework assignments. And if you have any questions on the recent material, please come and find me, and I'd be happy to talk it over with you in more detail.